Hi, folks. This is Stan Forster. We're in Module 5 right now. This is Life and Death of Stars. And we're going to study the stellar life cycle. Put it short, occasionally there are these shock waves that are traveling through well, not occasionally, there are shock waves traveling through the rim of our galaxy, that flat portion of our spiral galaxy. And as that shock wave goes through, it compresses these molecular clouds, these clouds that form up the disk of the galaxy, in addition to the stars that are there. And just by random chance, there are places where there's a little more density than there would be otherwise. Okay, and there's gravity associated with that mass, and that mass begins to attract itself and begins to compress itself. Now, this doesn't happen quickly. It happens over a very long time. Even though we're talking about temperatures that are in, 1, 2, 5, 6 Kelvin. Okay, that's still that compression causes that area to heat up, and it takes a little while. The pressure actually builds, and it takes a little while for that heat to radiate away, to be redistributed elsewhere, and for the compression to continue. So it's a very, very slow process. But what happens eventually as we begin to get clumps of this gas that begin to coalesce, and there are these little lumps inside there, and there are these little eddies and swirls, all this random motion gets concentrated in one spot, sort of like an ice skater who's, you've seen the ice skater go around and then they pull their arms in and they spin very, very quickly. Okay, and so all that random motion, some of that has a net rotational motion. And as you take those gases and you compress them in over thousands of astronomical units, this stuff begins to spin very, very quickly, and it begins to rub against each other. The stuff that isn't going the right direction, the same thing as everybody else, is being run into, and there's some friction. And even the things that are going sort of the same way, let's say you got a stream of material going this way, a stream of material going that way, as they're rushing past each other, kind of averaging out. They're averaging out their motion, and it's all flattening into a disk. But the net result is that there's a friction and there's heat generated. This whole thing begins to heat up, and the interior continues to compress and continues to give off heat till sudden, and gravity is winning here. Okay, but the center of that, at the very, very center of that, suddenly you get to the enough temperature, enough density, enough pressure that these protons moving together can begin to collide, begin to coalesce, and they begin to fuse, and they release energy. And that beginning of fusion, that's the birth of the star. Now, everything past this depends on how much mass was in the star when it was born. For a low mass star, our star, okay, it's going to sit there on the main sequence for a very long time. Like, for instance, our star is a G-type star, and it has a lifespan of about 10 billion years, and it's going to take that long to burn up the fuel in its core. And we're about halfway through that right now. Okay, but in another 5 billion years, what's going to happen is that our star is going to run out of fuel in its core. Okay, and just sort of think about a candle with that somehow it's got that little pool of paraffin there, and it's vaporizing it, drawing it up, and it's burning it. You get that release of light and heat. Okay, but imagine that paraffin had a little bit of water in it, something that wasn't paraffin, like when those hydrogens come together, what's burned, what's left is helium, and there's helium left over. It's contaminating that fuel source, and the whole thing begins to sputter a little bit. Okay, and the star becomes unstable. Okay, and as it begins to pulsate, it can begin throwing mass off. Those pulses can become sufficiently fast that it actually reaches the escape velocity of the star. And these big chunks of gas and mass are thrown off. These are mass ejections, and you can form a nebula from that. And that'll continue because as it's losing mass, it has less ability to hold on to the gas that's left and becomes even more unstable. And then eventually all that is left, and all you have left is the white hot core uh, that was left, and that's a white dwarf. If we talk about the big stars, though, we talk about the really big stars, uh, those burn very quickly. The our star has about 1/10 of its radius is the core, okay? But you have to reach that same depth on an enormous star. You reach it much quicker, and a bigger portion of the star is actually engaged in that fusion process. It swells up much bigger. Okay, but it's burning very, very quickly. It's sort of like a Maserati burning through its gasoline. It goes through that gasoline very, very quick. And it doesn't seem like it, but um, it just, when you think about it that way, that the actual core volume is so much a bigger percentage of the star, you realize that those stars don't live very long. Okay, if you go through our stellar classifications, O be a fine girl, and yes, O be a fine girl, and kick me. Yes, okay, we'll go with that. Kick me. Uh, the O type stars, the O and the Bs are going to go through their fuel in just a few million years. That's why we don't see very many of them. Well, one, they're not, a lot of them aren't formed, even in the process. Okay, think about it with just a random process when things break. You have a few big chunks and you have lots of little chunks. Okay, and that's the same thing that happens in a star forming. Okay, so you've got very few large stars that are born. They don't last very long. And so we don't see many of them. But if you want to see a few of them right now, go outside at night and look at Orion. Look at Orion. And then if there's a curve that some people call it a shield, some people think of it as a bow, and you can almost imagine that an arrow has been shot out. And if you look over there and look for that arrow, there's this fuzzy patch in the sky, and that's called the Pleiades. Some people call it the Seven Sisters. And interestingly enough, I look up there and I can't count seven stars. Um, but we have writings that refer to them as even more stars, like 10 sisters. So we know that at one point people were able to see more stars than ones we see now, and we no longer see those. And I don't even see seven. So, in any case, that is a former star forming region. Okay, it is. It was this huge chunk of gas and cloud and everything like that. The stars started burning. Started light pressure started pushing away that gas until suddenly the star forming region opened up, sort of like an egg, and it revealed all these new stars. And as it rotates around the center of the galaxy, um, those are going to spread out. But right now, they're still close, and we can take a look at that. You could also, let's talk about the very, very small stars, okay? The red dwarfs. Okay, now the definition of a red dwarf is called fully convective. It's a fully convective interior. Okay, I had to reboot English there. Okay, our star has a core. It has a radiative zone. It has a zone in which there's so much compression on, so much light pressure pushing out, so much gravity pushing in. Everything's locked in place. Nothing's moving. But a little further out, we have a convective core. This is when the material begins to move in a bulk fashion. You see bulk matter, hot matter, becoming hot and rising toward the surface, and stuff that's on the surface of our sun, okay, gives off its energy, and becomes cooler. Not cool, it's the surface of the sun, okay, but cooler than the stuff underneath, and it begins to fall down, and we have this convective cells that occur. And if you look at the surface of the sun and you use the right filters, you can actually see this mottled surface that and you can see the convective cells. It comes up in the center, and the edges of these cells look darker because the filters that we're using can tell the difference between just a few hundred degrees. This material at thousands of degrees. All right. And so the stuff on the edges is actually sinking down, and the stuff in the center is coming up. Well, a red dwarf star, the definition of a red dwarf star is that it is fully convective. In other words, that radiation zone where the light pressure is one way and the gravity is, the star is so small it doesn't have that zone. And what happens is that the convective zone reaches all the way into the fusing core, and that fusing core is continually being renewed. We're actually drawing the helium out, that stuff that would make it the fusion kind of go away or get poorer. It would be a poorer process. Okay, and we're drawing new fuel in, and so even the limits that we would think of as being the limits of the lifetime of big stars that burn very very quickly and small stars that are a little more modest, these tiny stars, they're going to have lifetimes that are measured not in billions of years like our own, but in trillions, which means that the universe hasn't been around long enough for us to witness the death of a dwarf star. Think about it. In a few trillion years, that's all that's going to be left is dwarf stars, because all the big stars will all have burned up. All the medium stars will all have burned up. They'll have formed new stars, but they will very quickly have burned out. And the only thing that'll be left are these little red dwarfs that are um, still chugging along. Okay. So just something to think about. Okay. That was sort of an overview of what we're going to be learning. Um, I'll see you all in the discussions. Okay.